Okay, so what was that? What was it? Yeah, so what's the big picture we're doing? Correct, yeah, that's what we wanted to do. So it's all about, this component, this inertial forces. And now the inertial forces is mass multiplied by acceleration. Acceleration, how it is written here, is going to be, is actually expressed in global coordinate system. No good, no good. Particularly no good because this one here is already expressed by using generalized coordinates. No way that they match, no way that they match. So we have to do the same procedure to inertial forces. And now, remember I explained that, when things becoming very complicated, I remember I made these drawings about the time, level of difficulty, and it goes it really goes up. And this is when it's going to happen. So now it's going to go up. Not because of the concept is so much different, but because mathematics is very involved. By saying that, I really would like you to focus on the big picture. Because as soon as you started to look at the details of the mathematics, oh my God, you cannot find a way from this lecture room. I can guarantee you that. It's going to be so confusing. So think about the big picture. Think about what is that we're doing. Why is that we're doing? And that helps. And really, if it becomes too hard, hold the hand of your fellow student and try to hang around, try to manage this together. Okay? So you need to move to closer together. So, okay? You ready? Okay, so let's make it happen then. Now we're going to take a look at again, inertial forces. Now the first difficulty comes here. Because instead of saying the mass of a particle, I want to be more sophisticated because, we would like to show off how good we are in physics. So instead of saying mass, we wanted to express the same thing but more sophisticated way. So we're saying that density integrated over the volume of something. Well, what's that? Well, that's going to be our mass. So the first important thing is that don't get confused about this, but because what holds is of course this relation. Mass is equal than the volume integral over the density within the boundaries of the body. So that's what it is. But so why is we do this? Because this is going to be more general. That's one reason. Another reason is that next time that you have a weekend off, you go home, you can show off to your mom and dad because you can tell, look, this is what I'm eating with my breakfast. So this is, generalized inertial forces. I'm very comfortable with that. And it looks very bad. Okay? Two reasons. The one that is more important is that really because it's more general, it helps us during the course of this derivation. Now, so we have inertial force, which is a mass multiplied by acceleration, and the mass is again expressed by using that volume integral. What I have here in the middle is acceleration. Now, this acceleration is expressed in global coordinate system because it is r dot dot. And r is a vector that consists of two components. These components are projection in a global x and y coordinate axis. Simple like that. Now, we're going to follow the concept of external applied forces. So we're going to just take these inertial forces and we're going to multiply that with the virtual displacement. Why? Again, because we desperately wanted to have this mapping between the global coordinates and generalized coordinates. Okay, so how it goes. So I have here delta R multiplied by inertial forces. And inertial forces in this time is expressed again in global coordinate system. Okay? Right, so, then if I want to use really substitute that information here, this is how it reads. So it's already become to be a little bit messy, but, keeping big picture in your mind. We have just virtual displacement, which is this mathematical miracle that we need to do this mapping. And then we have mass multiplied by acceleration. Nothing else. You still with me? Okay, good. Okay, so let's go. So then, what we're going to do, we're going to use this operation that we are very much familiar with. So, a little too early. So I don't know why it is always have to be this way, but it seems to be this way all the time. So, delta R and delta Q. It sounds like, but what's the difference that makes? The difference is this, that there are two set of coordinates, global and generalized. What relates these is this partial R, partial Q, which is the mapping matrix. Again, the mapping matrix. Now, I'm going to substitute that information to my previous equation. That's how it's going to be. I'm going to take the delta Q off from that equation. What is left is going to be called as generalized inertial forces. And generalized inertial forces can be written as it is shown here. What I have here is my mass multiplied by acceleration multiplied by my mapping matrix. Nothing else. Sure, in a second. So I have mass multiplied by acceleration multiplied by mapping matrix. Nothing else. Now we're going to go one slide up. You wanted to take a look like how is a big picture. Maybe there's a typing mistake. No typing mistakes. Are you developing the migraine when you're looking this? Is it like you're already feeling that my head is hurting like big time? No. Okay. But you all right? Others? I'm asking, are you developing a headache? No? It's good, because you have can-do attitude, right? So can we go? Okay. Now, prior to substitution, we have, because, we have to substitute certain information here. So we have to substitute, first of all, this mapping matrix that we already got from the case of external applied forces. But also we have to substitute our acceleration to this equation, this part. Now, prior to that substitution, I wanted to express my acceleration a little bit of modified way. My original way to express my acceleration is the one that is showing here. This is what we looked at, 3 weeks back. And we concluded that the acceleration consists of 3 components. And these components are translational acceleration, then tangential acceleration, and a normal acceleration. And this is the painful one, because it's quadratically related to velocities. And now the price we have to pay because of all these kinematics is right now, because we're going to have to deal with this complicated expression of acceleration that will be substituted to that previous equation. And it will lead to 2 different components. The one that is linearly associated to accelerations, another one that is quadratically associated to velocities. Let's take a look. Now, prior to this, look what I did. I'm going to collect my generalized accelerations. These are generalized accelerations. I'm going to put them in a one vector because, I can identify that here is one component associated to generalized acceleration. Here is another one. Oh my God, and I can see that there is a typing mistake because, and no, you're saying nothing because you knew this already like long time ago. Look, this is power 2. It shouldn't be power 2. And I tried to make it disappear. It shouldn't be power 2. All right, so I'm collecting this information, and I'm going to build this in such a way that I have like, the matrix, and then these are the accelerations. What is left is the component that is quadratically associated to velocities. Okay? And now comes the most painful part of this course, entire course, in your entire career of getting master degree, in your entire life. Well, at least say within the next, 2 to 3 years, this is it. So we're gonna substitute all these painful components to one big mess, and we'll see how it looks. First is acceleration with this definition we just looked at. So this is acceleration. So I have here this kind of like a multiplication matrix, and these are the acceleration of generalized coordinates, and then the component that is quadratically related to velocities. And then my mapping matrix, which we concluded that can be written like this. This will be substituted to this part of the equation. This will be substituted to this part of the equation. You still with me? Okay, so that's once I do this substitution, this is how it looks. So this is my mapping matrix. This is my acceleration. No further manipulation, mathematical manipulation, but soon I will introduce a bit more mathematical manipulation. So this is how it was originally. Mapping and then acceleration. So this is related to acceleration, this is related to my mapping. Okay, so once I do this operation, then I see that there is a component that obviously is a matrix, which will be multiplied by acceleration of what? Generalized coordinates. So here it is. Look at that. So, this is the way to explicitly express generalized coordinates. What do you say? You happy? Okay, so yeah, I'm sure this comes clear after a little while, but look what we have. So we have here something that is 10 multiplied by acceleration of generalized coordinates, not global coordinates, but generalized coordinates. And this is exactly what we want. And then there is another component which is that painful component, which will be called as a quadratic velocity vector. This is considered as a force, similar way that the mass matrix, this by the way is called mass matrix, multiplied by acceleration, is also kind of like a force. So these together is generalized inertial forces. The beauty of this is that now finally we have this particular component that we really wanted to express. So we can build our equation of motion and then solve acceleration, and not just any acceleration, but acceleration of generalized coordinates. Make sense? Good. Yeah, I know that, that you're thinking like, how much more is left? I can tell you that. Half an hour. So it's quite a long way to go. But this is when we are in a really up in a mountain. This is it. So next we're going slowly down from that mountain. So it's not going to be this bad anymore. So it was it. This was it. Happy? Makes you feel better? Good. Okay. Now, what we're going to do next is that we're going to take a look at these two components we just got. The one that is called mass matrix, another one that is called quadratic velocity vector. And that's it. Once we have those components, then we have equation of motion, end of the story. So that's it. So then we have everything we need, and I can just explain the steps you can create the equation of motion automatically. No thinking whatsoever. Okay, so let's go and take a look at the tenderized inertial forces. That's the way that we're going to look this one particular component that we obtain here. I think that I need to use this one here, which is a mass matrix. So mass matrix will have dimensions that are 3 by 3. Where that is coming? Because it is associated with tenderized accelerations. How many tenderized accelerations we have in a one body? Is 3. Okay, I was a bit unclear when I say 3 by 3. It's 3 by 3 for one body. So if we have 2 bodies, it's going to be, 6 by 6. If it is 3 bodies, it's 9 by 9, and so on and so forth. That's how it goes. But we look at how to build the whole system matrices a little later. Today we're going to focus on single bodies only. Okay? Any questions, by the way? Comments? Okay. Because that's what you were thinking all the time, that this is how it's going to end up anyways. So no surprises really, I guess. Okay, so let's go. Let's look at the mass matrix and quadratic velocity vector. Now, this is how the mass matrix will appear, and how I end up to have this. I need to explain this to you first. Once you do this, let me see if I can do it. Once you do this operation, which is, identity matrix, and this is a vector, you end up to have 3 by 3 mass matrix. How is this 3 by 3 mass matrix? How are the components? Well, they are listed here. And now what we're going to do is that we need to take a look. What is this mass matrix, and how is that we can build the mass matrix to any case, regardless where the body reference coordinate system is located at. Now I think that this is telling the inertial properties of the body with respect to body reference coordinate system. And it will be a function, it depends heavily where the body reference coordinate system is located at. Now, mass matrix consists of 3 different components. It is a symmetric matrix in such the way that, off-diagonal components that are, this one and this one, they are having the same numerical values. They are symmetric, which is a good news, mathematically good news. This is the first component. Then the component that is located in the upper left corner of the mass matrix, this is the one that will be associated to tenderized coordinates Rx and Ry. Those are translational coordinates. Now, if you think about the translational motion, how is the inertial forces in case of translational motion? So it's going to be mass multiplied by acceleration. So this one here, this component will be 2 by 2 matrix, which is a subdiagonal representation. Diagonal components will be mass of the body, because the mass of the body will be same regardless if you're moving this direction or this direction. It's all the same. Then the component that is located in the lower right corner, this one here, that is a mass moment of inertia. That is associated to tenderized coordinates theta. So it is resisting the angular motion, the rotational motion. And that's what the mass moment of inertia is doing. Its value depends where the body coordinate system is located at. Now, what is then the physical interpretation of this component that is here in upper right corner and the lower left corner? That's the one that couples the translation and rotation. And that's a little hard to understand this time, but in a way it is associated to our quadratic velocity vector. We will get back to that a little later, but details of these components are shown here. So the first one that is associated to translational tenderized coordinates is 2 by 2 diagonal matrix. Diagonal components are mass of the body. That's it. Because again, associated to translational motion. Then This one is mass moment of inertia. And you can compute that by using this sophisticated mathematics like shown here in a slide. Or alternatively, you can take a look at the pre-calculated tables. There are plenty of pre-calculated tables. The one will be available in a Moodle database. So take just the equation you need and use that to compute the mass moment of inertia. And then the final one, that's the one that will couple the translation and rotation. All becomes clear when we're looking at an example. And here's an example for you. So I have here a box-like body. And this box-like body is having the length that is denoted as L, and the height that is denoted as H. And the body reference coordinate system is located in the center of the mass, because you know that's how it is based on the figure. So it's the middle of that situation where, again, body reference coordinate system is located in the center of the mass. Well, the first component, we can do it this like really sophisticated way by using these volume integrals. But seriously, you don't need to do this hard way. You can just use a common sense and pre-calculated tables. But, you know, we're going to integrate the volume of the body. We're going to integrate the density over the boundaries of the body. And this is this volume integral here. I'm already giving you the thickness of the body, which is denoted as a W. And then I'm going to integrate within the boundaries of my planar body. And my boundaries are in x direction. Look at where the x is pointing. So in this one here, the boundaries are minus L divided by 2 to L divided by 2. Okay? And that's going to be my x direction. And then my y direction is h divided by 2, minus h divided by 2, h divided by 2. And that's that y direction. Rest is pure mathematics. Well, actually, no really mathematics is needed, because you know what's going to happen in this integral, the first integral. You're going to get the length here. So now is the density multiplied by length multiplied by thickness. And then the final thing, when you do this final integration, you're going to get density multiplied by height, multiplied by length, multiplied by thickness. And all that will be multiplied by 2 identity matrix. What is this? HLW, that's going to be the volume. Volume multiplied by density, what's that? Mass. So we're going to have a mass here that is multiplied by 2 identity matrix. We're going to get diagonal matrix where the mass of the body is located in a diagonal components. Clear? Then the component that relates translation and rotation, you know, I could use a common sense and tell that this is going to be equal to 0, because there is this special case where according to that special case, if the body reference coordinate system is located in the center of the mass, this component will be equal to 0. If you don't believe it, you can do the mathematics. So you can take this equation as it is shown here, and you can integrate the u bar over the volume of the boundaries of the body, and you're going to get the exactly same solution. So it's going to be 0, 0 vector. We're going to look at that in soon, and when I'm going to move my body reference coordinate system off from the center of the mass. Final component is my mass moment of inertia. I could use pre-calculated tables, but because I want to show off about my almost next to nothing mathematical skills, I wanted to do this hard way. Hard way is by taking this vector u bar transpose multiplied by vector u bar, that you can write as it is shown here. So it's a u bar x power 2, u bar y power 2, and that you can integrate over the volumes of within the boundaries of the body. Well, the thickness is already provided here. There's again W, and then you're going to do this integration from minus L divided by 2 to L divided by 2 in X direction, you're going to get solution that is shown here. And then you're going to do the Y direction. Oh, this dxy is missing here. Once you do that, then you're going to get again HLW, that's equal that the volume multiplied by density, that's mass, and that's how the final solution look like. Make sense? Now I'm going to repeat this, but with difference that I'm going to, this is the summary. I'm almost skipping the summary. So I'm going to have a diagonal representation of my mass matrix. So here is my submatrix that is associated to translation. This is my scalar component that is associated to angle theta. And this is the one that couples the translation and rotation. Okay. Now, I'm going to speed up a bit. I'm going to redo the whole thing, except I'm going to move my body reference coordinate system to one corner of this box-like body. And then I will ask you the in-class quiz. In that in-class quiz, listen to me. All my participants, listen to me, because I'm going to tell you the solution for my next in-class quiz. I'm going to ask this example again. I'm going to ask the case where the body reference coordinate system is located in the center of the mass. And I'm providing you the number of choices how the mass matrix can be. And it only can be the diagonal representation where the dimensions are 3 by 3. 3 by 3 because 3 generalized coordinates. Diagonal representation because the body reference coordinate system is located in the center of the mass. Please memorize this. Please. Put it in your notes. Put this in your notes. Like in this case, this is how the mass matrix will look like. Because the way the body reference coordinate system is located at, and because I'm dealing with the generalized coordinates. All right, so here is my second case. So this is the case where the body reference coordinate system is moved to one corner of the box-like body. Remember, the body coordinate system can be located anywhere you want. Within the boundaries of the body, outside of the boundaries of the body. It can be also located in the center of the mass. So it's no rules really. Okay, so how is it going to be? With no thinking, I'm going to just repeat what I just did in previous case. The difference this time is that the boundaries of my integration limits are different because how the body coordinate system is located. So how are the boundaries then? Well, the boundaries this time are, from 0 to L, because look where the body reference coordinate system is. So it's here. So when I'm traveling here to here, it's going to be 0 to L. This other direction is going to be 0 to H. And that's my only difference. How much this is going to change mass of the body? No change. The body mass is not going to change depending where you're going to put your body reference coordinate system. It will not change because that will be making no sense whatsoever. So if someone is saying that the body weight depends where you put your body reference coordinate system, that's nonsense. Is it going to change the mass moment of inertia? Yes, it will, because it depends, where you're going to rotate your system. Where's your reference rotation? Is it going to be in the middle or is it going to be in the one end? If it is in a one end, it is resisting more than in the middle. So it's going to change it because it depends where's your reference point when you're looking the rotation, and it will affect that. Where's the stick? Here. Look. You need to have a lot of muscles to do this, but I haven't. So no worries. So you can do it this, but you don't need that much muscles to do this. You can do that. This, I don't think. But it's a bigger, it's resisting more. That's all right because it makes it happen. All right, so now let's look how are the other components? This first component, no changes whatsoever. Clear? Because it's all about the mass of the body. Second component, which is a mass moment of inertia. Second component is the one that relates to translation and rotation. Now, this is a little bit painful component because really now what I need to do is that I need to do the math. I need to take this vector u bar, and I have to take the rotation matrix that is differentiated with respect to angle theta. And now I'm going to differentiate this component such the way that my integration limits are 0 to L, 0 to H. And when I do that, this is going to be non-zero. You can tell that already based on how it appears. When I do my first integration along the x direction, here is going to be L power 2 divided by 2. This is going to be u bar 2 multiplied by L. And when I do this y direction, this is how it finally appears. So it left me no other choice than, multiply everything that I have here with respect to my rotation matrix that is differentiated with respect to angle theta. This one here again is my volume multiplied by density, that's mass. Okay, so finally my solution consists of, is a vector of two components, and this is how it looks. Very important to understand this. This is because how my body reference coordinate system is located at. Mass is still gonna be same regardless of where your body reference coordinate system is located. This is, what couples the translation and rotation. That's why it is a function of angle theta. So the mass matrix is actually nonlinear and is a function of body orientation. The mass matrix representation is nonlinear. Okay. Final component is my mass moment of inertia. Again, I'm going to repeat all the same story that I did in a previous case. Going to integrate over these boundaries, 0 to L, 0 to H. And what will happen is that my final outcome will look like this. So it's a mass divided by 3 multiplied by L power 2 plus H power 2. Memorize this, because let's look how it was in a previous case. It was mass multiplied by 12. Other than that, the components were exactly the same. So which is highest? Previous case. Remember? The previous case, because that was mass multiplied by 3. This is mass multiplied by 12. Big difference. Clear? All clear. Okay, so let's go and check it out, the in-class quiz. In-class quiz is like follows. Oh, this is the summary. I'm putting everything together. So no surprises here. And my in-class quiz is this. So I'm asking, a figure depicts a triangular planar body with the body frame of reference that is coincident with its center of mass. Length, width, density are given. So what's going to be the mass matrix? And let me put the in-class quizzes on. Next, in order to enter your answer, you have to take a look at these options. Now let me read these options. So this is the option. I need to put this ink on. So this is an option that is having the matrix that is the dimension of 3 by 3. And then the upper left corner of the mass matrix is something that the mass of the body is located at. So it's a 2 by 2 diagonal representation. And then I have the components that couples the translation and rotation and mass moment of inertia. This is 3 by 3 matrix, which is a diagonal representation. This is 2 by 2 representation, and this is geosymmetric version of the previous one, which is correct. No comments. Okay. let me see what follows. Oh yeah, I figured you know what I'm planning to do today? I'm thinking that what do you say if we're gonna close right after that in-class quiz? After this? How that sounds? It sounds like the best idea ever. Because what I noticed, I don't know, maybe that's because of the technical difficulties, maybe because I'm slow, but I noticed that many of the classes are more than 45 minutes by 45 minutes. But that's, maybe that's a good news for you, so you can learn more with same amount of money. So it's a good deal. Okay, so what do you say? What's going to be the success rate of this in-class quiz? We got more and more students. Now is 90 students. Again, let me keep this on so to make sure that you can see what are the options. So what? Yeah, but how are you gonna make it happen? Can you in a streaming? Can you in a YouTube streaming? Can you go back? Yes. You can, really. So this is for online participants. This is a little bit of cheating. That's all right because we are so strong. We don't need that kind of cheating. We know by heart what it is the correct answer. Okay, so let me take a look. 73 students. Is you guys already entered your answer? Back row is you still awake? Is all good? He's like, no idea. At least I have no idea what's the correct answer. Can we take a look? 77. So it seems to be that. Okay. So is today? Is it going to happen today? No, I don't think so. But I'm hoping that some of the stupid answers are not worded at all. That's where my hope is. 90. Oh, that would be really good. 96%. 96. That would be all-time record, isn't it? I think it is very close to that. Okay, so seems that we got no more answers. So 90 students. Okay, ready? Oh, look, almost. This was like this close to get the all-time record. Very close. 94. The good news is this. Yeah, but you know, what is a really very good news is that not really many votes is going to this. Oh, no, I need to change this. C, it only got like, was it 4%? So that was really good news. This was voted no, single time, because this makes no sense. Skew symmetric representation of matrix, like what is that? Makes no sense. Now, the correct answer is this one, because where the body reference coordinate system is located at. So it's located in the center of the mass. Now what follow is that there will be next Monday, there is going to be a short explanation about quadratic velocity vector. It's going to be like the one that is shown here. Is we're going to take a look at this one particular component that is shown here. We're going to look how it appears. I'm going to provide you the physical interpretation of it, and that's it. Then we are ready to write the equation of motion. Remember when I expressed this kinematic, these awesome kinematics about this one body that was moving, and then even more than that, there was two bodies that were moving. Now we're going to do the dynamics. So it's going to be really the highlight of your career. So we're going to solve the dynamics by using the 6 steps that everyone can take. You ready to do it? Because it's going to happen next Monday. Be here. Okay, so let's close for today, and hope to see you on Monday because it's going to be just outstanding. Thank you.